Hey there. So this video is going to be about what we call numerical integration. And if you remember, so what have we been doing so far in this chapter? This chapter has been all about techniques for integrating, right? And the reason for that is because we know from the fundamental theorem of calculus that if we want to evaluate an integral that looks like this, right? A definite integral from a to b of f of x dx, then it suffices to look for an antiderivative and evaluate that antiderivative at the endpoints. Now, the problem is there are actually integrals for which we can't do this, right? For instance, the integral of e to the x squared dx, right? Or the integral of sine of x cubed dx, right? These functions do not have what we call elementary antiderivatives, in the sense that there's just no answer here in terms of these functions that we know of. And so in order to even calculate these integrals, well, we have to go into some numerics, right? Maybe using a computer or using something else, we can actually get an accurate enough approximation to what this exact value is. So I'll give you some examples first, and these are things that you've seen before, right? So for instance, the integral from 0 to 2 of e to the x squared over 4. Okay, so again, this is an example where we can't find an elementary antiderivative. So, well, one thing you could do here is to use your Riemann sum approximations. And let's say using n equals 2 for now, what do we get when you use the left endpoint sum, right? The left endpoint approximation. So I'm going to call that L sub 2 here, right? And in terms of our drawing here, it's going to look like this, right? We split your interval up into two subintervals for 0 to 1 and 0 to 2. Take the left endpoint of each subinterval and use that to draw these rectangles, right? And so the left endpoint approximation is going to be equal to the total area of both these rectangles, which is equal to 1 times the left endpoint, which is, so it's 0 here, right? So that's e raised to 0, which is 1, plus 1 is the width of the second rectangle, multiplied by e to the 1 over 4. Right, and so that's one approximation. And we can go a bit further, right? You can do n equals 4, for instance, and you'll do 1, 1, and then 1 times, well, now you're going to get something here. That's 0.5, it's e to the 1 over 16, right? And so on. So you know how this left endpoint approximation works. Now, another thing you could do is to use the midpoint approximations. Right, and again, how that works is, instead of looking at the left endpoint or the right endpoint, you're going to use the midpoint of each subinterval to tell you how to take the height of the rectangle in that subinterval. Right, so it's going to look like this. And I'm going to call that M sub 2 for midpoint. And the width of each rectangle is the same. It's still your delta x here. So for 2, delta x is equal to 1. But now it's e raised to 1 over 16 plus 1, e raised to, so that's 3 halves, right? Which is 9 over 4, so that's 9 over 16. And we already saw that we can use these rectangles and just let n go to a very large number to get something that's more accurate, right? You can do left endpoints, right endpoints, or midpoints in this applet. And you'll actually see here that using midpoints, even though we can't evaluate the integral in the sense of looking for an antiderivative, well, at the point that we have n equals 256 rectangles, you see that the midpoint approximation, 2.9253, is, well, it's indistinguishable from the exact value, 2.9253. in the sense that if we're only looking at the first 4 decimal places, then that's good enough, right? It's practically the exact value if you only care about until the 4th decimal place. And so what I want to do here is to give you another rule that we can use in order to do these approximations, so that we'll have 4 rules after this: left endpoints, midpoints, right endpoints. And so what's this other rule? Well, let's generalize the formulas here first. So L sub n, we know, that's going to be equal to delta x multiplied by f of x sub 0 plus f of x sub 1 until f of x sub n minus 1, right? If you're taking n subintervals. Our n starts at f of x 1, and so on, and ends at xn. Right, so x sub 0 here, that's your a. X sub n is b. And each x sub I here just denotes the endpoints of each interval. Right, so the ith subinterval. Right, this is just a review at this point, right? Ith subinterval is xi minus 1 to xi. And so, okay, yeah, so midpoint as well. So that's going to be delta x times, we'll take the midpoint, so that's x0 plus x1 over 2, x1 plus x2 over 2, and so on. Right, because the midpoint here is just going to be xi minus 1 plus xi divided by 2. Now, what's the 4th rule, right? What's the trapezoidal rule that we talked about in the title of this video? So say we wanted to approximate the area in this manner, where instead of using rectangles, where their width is a given and the height is given by some xi star, why don't we do something like this, where we use information of the left and the right endpoint to give us something like this, where the area approximation is going to be the area of this region here plus the area of this region here, where we've used a segment to connect the function values at the 2 endpoints, the left and the right. And so using this rule, we're kind of following the path of the function here, right? So how do you compute the area here? Well, again, as I mentioned in the title of this video, this is a trapezoid. And we know that if you have a trapezoid, so what is a trapezoid in the first place? Right? It's a 4-sided figure with 1 pair of parallel sides. And so if you have these sides are parallel, if the height, or I guess it's on its side, so I'll call this the width of the trapezoid is delta x. If one edge here has b1, the other has b2 length, then the area here is going to be delta x multiplied by the average of those 2 side lengths. Right, so you probably remember this formula as something like this instead, from high school or from wherever, from grade school. Right, b1 plus b2 over 2 times h. Right, but here it's on its side, and you have delta x as the width. Right, and so what does this give us here? Well, for this specific example, what I'll call t sub 2, which is the trapezoidal rule with 2 subintervals. Well, I'm still going to have delta x here as the height, or I guess the width of each trapezoid. And now I'm going to use the function value at the left endpoint and the function value at the right endpoint, and take the average and multiply by the width. Right, so this f of x sub 0, that's this height. And f of x sub 1 is this other height. And do the same thing for the second trapezoid, and you're done. right? And so it looks very similar to the midpoint rule, right? But for the midpoint rule, you're taking the average before you evaluate the function. Whereas for the trapezoidal rule, you evaluate the function you evaluate the function at the endpoint and then take the average. And this is actually quite interesting because you can actually rewrite this and you can check this for yourself. And you'll see that this is actually the average of L2 plus R2. And that kind of makes sense, right? Because for each trapezoid here, its area is basically going to be in the middle of the areas that you get when you just use a left endpoint and get a rectangle, or just use the right endpoint and get a rectangle. And you can also see it from this expression over here. Right, and so that's another rule that we can use that's useful. And so let's formalize this here. If you have t sub n to denote the approximation of your integral from a to b of f of x dx using n subintervals, then that's how you compute the trapezoidal rule approximation. We've basically factored out the delta x here. You're counting f of a and f of b once and all the endpoints in between twice. Or probably easier to do, just remember this is just the average of the left and the right endpoint approximations. And so let's do one example here, kind of to compare the accuracy of the trapezoidal rule and the midpoint rule. Let's say we have the function cosine of x squared. So this is the graph of cosine x squared here from 0 to 1. And we'd like to use both of these rules to approximate the value of this integral from 0 to 1 using n equals 4 subintervals. All right, so that's your b, and then that's about in the middle, something else here, and something here. Okay, so midpoint rule. Okay, let's do the trapezoidal rule first. What's t sub 4 here? Well, x sub 0 is 0, right? That's your a. And then x sub 4, that's 1, or b. And how about the others? So this is x sub 1, 0.25. This is x sub 2, 0.5. X sub 3 is 0.75. And remember, you can always compute this by just using xi equals a plus I delta x. Right? And so delta x here is equal to 1 over 4. Okay, so what does the midpoint rule tell us? Midpoint rule says it's delta x for the width of each rectangle. And you're just factoring that out of the expression. That's the sum of the rectangle's heights, which is given by the midpoints in each subinterval. So that's cosine of the midpoint here, which is 1 over 8. So I'm going to use fractions just to make it easier. 1 over 8 squared. Here it's 3 over 8. Here it's 5 over 8. So yeah, I'm going to simplify this just so I don't have to deal with the powers here. And finally, 7 over 8 for the last interval. Now using the trapezoidal rule, it's just, again, the average of left and right endpoint approximations. Right, so the left endpoint is, so let's compute that first. It's cosine 0 plus cosine 1 over 4 squared plus cosine 1/2 squared plus cosine 3 over 4 squared. Right endpoint, similar. Right, so you already see the pattern there. You're taking the 3 in the middle and either taking A or B, depending if it's left or right. And so the trapezoidal rule is just going to be the average here, whatever that is. But now the computation's not that exciting here, right? But there's also a question here that asks, are these answers underestimates or overestimates? And you can probably visualize that for the trapezoidal rule here, you're actually going to get an underestimate. Because when you connect the corresponding endpoints in each interval, you're always going to get a segment that lies below the curve of cosine x squared. Right? So these segments are below the curve. And the reason for that is because cosine x squared on this interval from 0 to 1 is concave downwards. And so as long as it's concave downwards, when you use the trapezoidal rule on any interval, it's always going to lie below the curve. Right? So it's an underestimate. But what happens if you use the midpoint rule? So the midpoint rule, that's going to give you a rectangle of this height. And you see that that actually gives you an overestimate here. Right? Like I'll draw something here. If you have a function that's concave downwards and use the midpoint rule, you're always going to get something larger than what the actual value of the area is. So the midpoint rule is an overestimate. And that's actually nice here, right? Because that tells us that the actual value of the integral is somewhere in between t sub 4 and m sub 4. So t sub 4 is less than or equal to this value, which is less than or equal to m sub 4. And so I just want to end this video by asking you, can you think of some other way to approximate these areas, right? So you've seen the left endpoint approximation, right endpoint, midpoint, and now the trapezoidal rule. Can you think of another way to do the approximations here? Right? What if I gave you the graph of some function and asked you to compute the area, right? What would you do in that case? And how would you systematize that?